All right, so in the last video we learned this interesting fact. The length of the cross product of A and B is equal to the length of A, length of B, times sine theta, where theta is the angle between A and B. So I want to think through the significance of this with you. Sometimes the significance of these things can not be obvious at first glance. So I want to think about when A and B, when two non-zero vectors are actually parallel. So let's doodle for a minute. So here's A maybe and here's B. They're parallel when either they point in the same direction or maybe they point in opposite directions. They point in the same direction if the angle between them is 0. I'm again using theta as the angle between them. Or if they're pointing in opposite directions and you were to slide this vector over there, then technically the angle between them is now 180 degrees. So we'll say theta equals 0 or pi. All right, well, but in either case, whether theta is 0 or theta is pi, you can conclude that the sine of theta equals 0, right? Because if theta is 0, then sine theta is 0. If theta is pi, sine theta is 0. But if the sine of theta is 0, using this formula, you know that the length of the cross product is 0. So two vectors are parallel if and only if the length of their cross product is 0. But there's only one vector that has length 0. That's the 0 vector. If the length of A and B is 0, then you can conclude that A cross B itself has to be 0. I think I said if the length of A and B. I meant A cross B. If the length of A cross B is 0, then A cross B has to be 0. And so that's our sort of key fact, is that, let's copy this to save time here. A and B are parallel. Let's put it all together. A and B are parallel if and only if their cross product, and I made a mistake above, their cross product is the 0 vector. So this should be a scalar because it's a length, and this should be a vector because it's a vector. All right, so that's our first interesting observation. We can use all that nasty computation that we did up here. We got this nice clean result, and now we have an easy way to check whether or not two vectors are actually parallel. Now I want to completely shift gears and just consider what seems like an unrelated question. So think with me. If I take two vectors, A and B, and I'm assuming in this case that they're not parallel, although my formula that I'm going to get works, but let's assume they're not parallel, then I have an associated parallelogram. Do you see it? You can take a copy of B. Let's just do that. Let's just copy B, and you can slide it over here, and let's actually change the style so that it's green. Yeah, you should be able to see that. And then you can copy A, and you can slide that up right there, and let's change the style again so that it's green as well. And now you've got this parallelogram, and so I'm interested in finding its area. How do you do that? Well, let's think about it. The area of a parallelogram, I'm going to drop a vertical down here, take a projection if you will. So this is, I'm going to say, my height, and I know that the area of this thing is the area of, think with me, what is it? It's the area of the base. So it's the area of the base, or sorry, the length of the base. So it's length of A times, and then the height h. So the area of this thing is still just base times height. And now I want to ask myself, what's the height of this guy? Well, think with me. Let's just observe that the sine of theta is opposite, which is 8 over opposite over hypotenuse. So h over the hypotenuse, which is length of b. And so the point is, we know what h is. H is sine theta times the length of b. I'm going to write that as length b sine theta. And so the area, here we go, the area of the parallelogram associated to A and B is A equals, we've got it right here, length A times the height, which we said was length B sine theta. Well, la-di-da, no big deal. Wait a minute. We've seen this before. This is exactly the formula for the cross product. And so this is none other than the length, sorry, not the formula for the cross product itself, the formula for the length of the cross product. And so it turns out that this number, this length of the cross product, has a very nice geometric meaning. Anytime you compute the length of a cross product, you're actually computing the area of whatever associated parallelogram you have. So let's end this video at this point. In the next one, we're going to look at how to interpret some interesting products in terms of a volume, and then we'll be done with this section.